before we move into logistic regression and HLM a little bit. So these two, I want to elaborate on them a little bit more. And again, this idea of these specification errors. And actually thinking about it, I'm not sure he actually uses the term specification error in the book. But that's a generic term for these ideas that you've mismodeled the data. Keith does talk a lot about the issue of common causes, the importance of including common causes. And we've previously talked about this. You need to include the common cause. If you don't have a variable, if there's a variable that influences your predictor of interest and also influences the outcome, if you don't include it, your regression coefficient is going to be biased. Because either the direct effect is, if it's this way, this predictor, some of the effect of that common cause is being credited to your variable when it shouldn't be. And if you flip these around, part of the problem is, well, the direct effect is going to be bigger than it should be because you're overlooking the effect through that. Well, that wouldn't be a common cause, would it? So that wouldn't be its issue. But so in this case, again, the common cause, edit that out of the video. The issue with the common cause, it will bias your results, your regression coefficient if you don't have it. Now, Keith makes the point that you don't have to, on the other hand, if it's not a common cause, if it's something related to the outcome, but it's unrelated to your other variable of interest, you don't have to worry about it because it won't bias the regression coefficient. And we saw with the Venn diagrams, what happens is there's no overlap between this variable and that variable in the Venn diagram, so whether it's in there or not has no impact on your regression coefficient. That's why we like random assignment and equally balanced the cell sizes and everything to help make sure things are uncorrelated. So he's absolutely right that a variable, a predictor that is not a common cause, even if it's related to the outcome, if you don't include it, you don't have to worry because it won't bias this regression coefficient. However, it's not quite that easy. It's not quite that convenient. That by excluding it, your standard error here will be larger. If this accounts for a lot of that variance, a lot of the variance in the outcome, and in essence, if you've got these other predictors that can take a big chunk out of that variance in the outcome that's unrelated to this effect, it becomes easier and easier to detect the effect of your variable. So even though not including it doesn't bias the results, if there are some variables that are uncorrelated, that's not a common cause, that are pretty big predictors of the outcome, you may want to include them because it'll make it easier to detect this effect. And you'll see people design studies that way on purpose. That it's like, this might be a very small effect. And I want to detect it, and I anticipate it'll be a small effect, so let's find some stuff out here that's going to soak up a lot of that variance. And that'll help me to detect what might be a small path there. So I want to kind of put a little twist on Keith's point, but he's absolutely right that it doesn't bias the results, but it may still limit your findings if you don't have them. Including irrelevant variables, this is really, it's not going to bias your results if you've got a bunch of non-significant variables. But it can give you larger standard errors, which we'll see in a few minutes, which can be a problem. And you're going to lose degrees of freedom because you've got all these additional variables in the model that aren't doing anything for you. So it's not as big of a problem as excluding important variables, but it generally should be avoided. Other ways you can see specification errors is the model, do you have the, is your model, do you have the proper model for the data, for what's happening? And that's this idea that if it's a curvilinear effect, makes you need to include a curvilinear variable. You need to include that quadratic term. You can have nonlinearity, and this is a bigger problem. This is when you get into this. You could have a regression equation that's e to something like this. Ooh. This would not be. This would violate that very first assumption. This would not be a linear model. But you may have something that looks like this. I think I talked about the example of looking at drug use in kids. And whatever, I can't even remember what their outcome was. And I think it was something, they applied this model and found this little uptick that, oh look, people who were abstinent of drugs had problems. And it was best to do a little experimentation because they applied a curvilinear model. I would bet dollars to donuts what it was a truly nonlinear model. And it was just flattened out. That a little bit didn't, it's not that abstinence hurts you, it's just that a little bit didn't hurt you. But they applied the wrong model, which would be a specification error. I guess I should be forgiving because I've never looked at their data. Maybe they were right, I don't know, but I just had that feel for it. There's no question you're going to see that. If you put the squared term and it's flat, you are going to see the curve. You can have floor effects. Same sort of issue here, but that it's not really leveling off. It's just that you don't have variables that detect. You've kind of hit a. You don't have your variable isn't sensitive enough to detect below 0. So I might be looking at behavior problems, and a score up here is your violent crime, breaking an entry, skipping school, or not skipping school, drug dealing. And then skipping school, I don't ask questions about small behavior problems. And so you get a bunch of piles up at the bottom because it's not that it's truly leveling off, but my scale, for some reason, I just cut off too soon in my scaling. So that's one issue with scale development, which we need a course on scale development. Wouldn't that be nice? Mm-hmm. It's something you want to think about. You may, in scale development, you may include items that seem kind of ridiculously silly because you want to just make sure you don't build in an artificial floor. I mean, so these are other specification errors you might see. Detecting specification errors. Irrelevant variables is easy. They're just not significant in your model. And you can look at kind of the simple correlation. They're not related. They're not correlated. You put them in the regression equation. They're not correlated. So it's kind of easy to detect the irrelevant variables. Curvilinearity is easy to detect. Just throw in a quadratic term and see what happens. Is it significant or not? Or a cubic term if you think there might be that sort of leveling off. Interactions, we can just test. So again, we know how to do that. Excluding relevant variables, that's a lot more difficult. How do we know if I've left out an important variable? Well, if you have the data, you could put it in the model and test it. But if you don't have the data, which is probably why you would be excluding an important variable, I mean, hopefully if you've got the data and it's important, you know well enough to put it in the model. But if you don't have the data, there's really no way to test it, and that comes down to theory. You need to understand the literature. You need to be ready when your committee member challenges you on, well, you did all those surveys, why did you never ask parent education? You need to have theory is ultimately your guide for making sure you've included the relevant variables, particularly if it's a common cause. Types of measurement error.